Hey guys, in this video we're going to be looking at some really hard questions that could come up in your AQA Chemistry Paper 1. I'm going to take you through how to do the questions, how to break it all down, and then I'm going to take you through what sort of things the examiners are looking for. Here are the questions we're going to be going through in this video. Some of these questions may seem quite simple, but there are some of them that have quite a few layers to them, so you have to do quite a lot of work before you can actually answer the question. I'm going to take you through how to answer them and what sort of things you'll pick up marks for. Using a diagram, describe the structure of a calcium atom. So we can see from our periodic table that calcium has a mass of 40 and an atomic number of 20. It doesn't matter which way around they are, it doesn't matter where they're located, just as long as the larger number is the mass number and the smaller number is the atomic number. From this, we know that it has 20 protons, 20 electrons, and 40 minus 20, 20 neutrons. We know that protons are in the nucleus, and neutrons are in the nucleus, and electrons are in shells. If we look at our periodic table, calcium is here. That is in group 2. Being in group 2 means it has 2 electrons in the outer shell. It is in period number 4 down here. 1, 2, 3, 4. And that means it has 4 shells of electrons. So we know that the first electron shell can have 2 electrons in it, and we can see in the periodic table that period number 1 has 2 electrons. The second period has 8 elements in it, so it can have 8 electrons. Third shell has 8 elements in it, so it can have 8 electrons. So we fill up our shells going 2, 8, 8, and then we only need to know up to calcium for GCSE, so we go 2. So we start from the middle, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let's mark this. We have given the number of the subatomic particle and the location. So for the number and the location, we're going to get 2 marks for that. Again, for neutrons, we've worked out the number of the specific subatomic particle and we've given the location. And then for electrons, we've worked out the number and we've drawn the correct arrangement. So the correct number of electrons and then the correct drawing of the electrons. 3 made-up transition reactors were reacted together. Chromium oxide was reacted with pure cobalt and nothing happened. But when chromium oxide was reacted with pure hard-boiled, a reaction was seen. Give the order of reactivity and explain your reasoning. Predict what would happen when hard-boiled oxide is reacted with cobalt. So I've highlighted the reactions. So we have chromium oxide plus cobalt. That means no reaction took place. And because no displacement reaction took place, we can say that chromium is above cobalt in the reactivity series. If cobalt was more reactive than chromium, it would have displaced it. When we react chromium oxide with hard-boiled, we do get a reaction. This is going to be a displacement reaction. This question is seeing whether you can work out the order of reactivity given a set of data. Now, because a reaction was seen, that means hard-boiled is more reactive then chromium. So we can come up with our reactivity series. Hard-boiled at the top, chromium, and then carbontium. Now the last part of the question. Predict what would happen when hard-boiled oxides is reacted with carbontium. From the reactivity series that we've worked out, we can see that hard-boiled is more reactive than carbontium, so there would be no reaction here. Carbontium cannot displace hard-boiled from its oxide, so there will be no reaction. You don't have to write a lot of things, get a lot of marks on here because there's quite a lot of logic, there's quite a lot of thinking involved in this question. You couldn't come up with a full answer, a fully explained answer, unless you had worked out the reactivity series, which involves quite a lot of thinking. So we're going to get marks for working out, because there's no reaction, that chromium is going to be more reactive than carbontium. We're going to get marks for working out the products of the reaction and working out the reactivity series, and another one for putting it all together. And then lastly, using that reactivity series to work out what would happen in the predict part at the end of the question. Describe the differences in structures of diamond and graphite and explain how this relates to their properties. Here we have the structures of diamond and graphite. Here is diamond. You can see it's got much larger structure than graphite. You can see that the black bits here are the carbon atoms, and again over here the black bits are the carbon atoms. They are both pure carbon. However, diamond makes 4 carbon-carbon bonds. Whereas graphite makes 3 carbon-carbon bonds. They are both giant covalent, but because diamond makes the 4 carbon-carbon bonds, it is going to be hard and strong. Whereas because graphite makes 3 carbon-carbon bonds, it is going to have layers, can slide, which means that graphite is going to be soft. Because it makes 3 carbon-carbon bonds, there is a spare electron. This spare electron floats around in between the layers, which means it can conduct electricity. Whereas diamonds cannot conduct. They are both going to have high melting points and boiling points. That means they're going to be solid. Now if we look at the mark scheme, this is really, really key that we've got 3 carbon-carbon bonds and we've got 4 carbon-carbon bonds, and they are giant covalent structures. Carbon has layers, which means it is soft and it can conduct electricity, whereas diamond is hard and cannot conduct electricity. The next question is about metals. Why are alloys hard and why do metals conduct electricity? The one about alloys and pure metals is a really, really common question. Pure metals have layers. Layers can slide across each other. If the layers of metal can slide across each other, it means they're going to be soft. Alloys have different things in them. They are not pure, which means there are no layers. If there are no layers, they cannot slide and it is hard. So pure metal has layers. Layers can slide, making it soft. An alloy has no layers or disrupted layers, which means it can't slide, making it hard. Metals can conduct electricity because in a pure metal we have positive atoms in a sea of free delocalized electrons, and if these electrons are able to move, then that is the flow of electricity. So we have positive metal atoms in a sea of delocalized electrons, movement of electrons, is the flow of electricity. So for answering the question, why are alloys hard? Because they have disrupted layers, which means they cannot slide, so they are hard. Why do metals conduct electricity? There are positive metal atoms in a sea of delocalized electrons, and movement of electrons is flow of electricity. How much zinc carbonate would make 97.2 grams of zinc oxide? This question is quite a short question, but there are quite lots of things to do. First of all, we have to work out the formulas from knowing your ions of zinc carbonate and zinc oxide. Not only do you need to know the formula for the ions, but you need to know how to put them together. So zinc carbonate, zinc is Zn2+, and carbonate ions are CO3 2-. I know it's horrible that you have to learn this. Zinc, Zn2+, and oxide is O2-. We need to have them together in a 1-to-1 ratio because we've got 2 positives and 2 negatives. So zinc carbonate is going to be ZnCO3, and zinc oxide is going to be ZnO. We can see from the equation that zinc carbonate to zinc oxide, and then we're going to have carbon dioxide as our other product, but we don't actually care about the carbon dioxide for this question. Now we need to go to our periodic table and work out the MR of everything. So zinc is 65, and there is one of them plus carbon, which is 12, and there's one of them plus oxygen, which is 16, and there are 3 of them, giving us a total MR of 125. Zinc again is 65, and there's one of them plus oxygen, which is 16, and there is one of them, giving us a total MR of 81. So that tells us that if we had 125 grams of zinc carbonate, we would make 81 grams of zinc oxide. But we do not want to make 81 grams of zinc oxide. We want to make 97.2 grams of zinc oxide. And we need to find out how much zinc carbonate will make that much zinc oxide. So to do that, I'm going to pop a 1 in there. Now to get from 81 to 1, we divide by 81. So we have to do the same over the other side, divide by 81, giving us 1.5. Now do not clear the number on your calculator, keep the number on your calculator. To get from 1 to 97.2, we need to times that by 97.2. So we need to do the same over the other side, times 97.2, which gives us an answer of 150 grams. You can self-check your answers a little bit. This number here is bigger than this number here, and this number here is bigger than this number here. If you'd done your maths the wrong way around or got confused or upside down, then you might not get the numbers in the right ratio. So for this is quite a lot of marks for working out the formula of things, marks for working out the MR, doing the various different bits of the calculation, and then for getting the final answer. There is quite a lot of maths in this, so to help you out, I've written you a rather chock-packed full of questions book which has loads and loads of maths and chemistry for you. Explain what happens at each electrode during electrolysis of aluminium. So here we have our cell. It is slightly different to standard electrolysis setup, which makes it a bit trickier. We have our negative electrode down the bottom here, and this is where the aluminium ions are attracted. When they are at the negative electrode, they are going to pick up 3 electrons and they are going to turn into aluminium atoms. If we use our oil rig, aluminium ions have gained electrons, so they are being reduced. The aluminium can then be removed as a liquid. At the positive electrode, we are going to get the oxygen attracted. We are going to have the oxygen ions turning into oxygen gas, and they are going to be losing electrons. Now we need to balance that. We have 2 oxygens, which means we need 2 oxygens. There is a 4 negative charge, so we need a 4 negative charge there. They are losing electrons. This is oxidation. The electrode is carbon. Reacting carbon with oxygen will turn it into carbon dioxide, so it will wear away as carbon dioxide is lost. The important things here are the equations, oxidation and reduction, and what happens. There are quite a lot of layers to this question. Calculate the energy change when methane burns completely in oxygen. So first of all, we need to work out our equation. Methane plus oxygen. You should know that the products of combustion are water and carbon dioxide. We can then turn that into a chemical equation. So methane is CH4 plus oxygen turns into water plus carbon dioxide. We then need to balance that. And then it's a good idea with these equations to actually draw out what you have. And we have 2 oxygens, so I'm drawing that twice. 2 water, so I'm drawing that twice. And carbon dioxide. So we can now draw a line down the middle, list the bonds that we have. So we have CH bonds, and we have oxygen-oxygen double bonds. Over here we have hydrogen-oxygen bonds, and we have oxygen-carbon bonds. Each carbon-hydrogen bonds, we can see from the question, has a value of 413. Oxygen-oxygen bonds, 498. Oxygen-hydrogen bonds, 464, and oxygen double bonded carbon, 805. Then we need to go through and count how many we have. So carbon-hydrogen bonds, 1, 2, 3, 4. Oxygen-oxygen double bonds, 1, 2. Hydrogen-oxygen bonds, 1, 2, 3, 4. And then oxygen-carbon double bonds, 1, 2. This is why it's a good idea to draw it out so you can easily visualise the bonds and how many of each you have. Now we need to do the maths. So 413 times 4 is 1652. 498 times 2 is 996. 464 times 4 is 1856. 805 times 2 is 1610. We can then add those together. So 1652 plus 996 gives us 2648. 1,856 plus 1,610 gives us 3,466. We can then take the total energy for the reactants and minus the total energy for the products, which is going to give us minus 818 kilojoules per mole as the energy that is released. Now we can see here this has a negative value. You know, negative things are exothermic. And this is good because this is a burning reaction, and burning reactions are exothermic. So this is just another way you can double check your answers in the exam. If you've done the calculation the way around and started off with 466 and then minus 2,648, you would have got a positive value, which would have been endothermic, which would have been wrong for the question. So for this, you're going to get marks for the equation. You're going to get marks for each side, working out what things are. You're going to get a mark for the negative sign, a mark for the actual value, and a mark saying it's exothermic. Titration methods are very particular. You need to make sure that you're spelling things correctly. So here you're going to get a mark for spelling burette correctly, and then you're going to get another mark for spelling pipette correctly. It's one of the few places in chemistry where your spelling actually counts. So you need to pipette 25 centimetres cubed into an alkaline to conical flask, add phenolphthalein. It doesn't really matter whether you add acid or alkaline to conical flask, just as long as you remember to add the other one into the burettes. You can also use methyl orange as an indicator. You need to make sure that you state that it is of a known concentration if you want to be getting more marks. The initial reading is important, and then you need to make the first permanent colour change, and then you need to repeat the titers until they are very, very close together. What is the difference between strong and weak acids and high and low concentrations? Here we have strong acids and here we have weak acids. The green bits are our acid particles and the purple bits are our alkali particles. We can see with our strong acids that the acid and the alkali have fully dissociated. So the characteristic of a strong acid is that it fully dissociates. Which means if you put it into water, the hydrogen ion will separate. Whereas if we look at our weak acids, we can see some of them are still together and some of them have dissociated. So weak acids partially dissociate. Down at the bottom we have concentration. So here we have a low concentration and here we have high concentration. We are looking for the concentration of the acid compared to the water. Now at a high concentration there are lots of acid molecules in a set volume of water. So a high concentration has lots of acid to water particles, or a high ratio, whereas a low concentration down here you can see there aren't many acid particles in here. So a low concentration has a few or less acid, or a low water to acid ratio. So we need to get our wording good on these. Explain the difference in reactivity between group 1 and group 7 elements. So group 1 is over here and group 7 is here. And the characteristics being group 1 or group 7 are related to the number of electrons in the outer shell. So everything in group 1 is going to have 1 electron in the outer shell, and everything in group 7 is going to have 7 electrons on the outer shell. So here we have two elements, sodium, which is in group 1, and chlorine, which is in group 7. Sodium has 11 electrons and chlorine has 17 electrons. So I'm just going to fill those in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And it is these outer electrons that we need to be paying attention to. The nucleus is positive. It doesn't really matter for the moment what these are. You just have to remember that the nucleus is positive, and there is an attraction between the positive nucleus and all of these electrons. And for group 1, this positive nucleus is trying to hold on to this electron, but it's not doing a very good job because there's lots of things in the way. There's lots of shielding. And because there are other electrons in the way, it is easy to lose this electron because it's the only one there, and the more electron shells we get, the harder it is for the positive nucleus to hold onto it. So reactivity is going to increase as we go down the group. Because the more shells, the harder it is for this electron here to be held in by the nucleus. Now, when we're talking about group 7, we still have the positive nucleus and we have this gap here. And the nucleus wants to bring in an electron to fill this gap. But again, we have this shielding. And the more shells there are, the harder it gets to fill. Which is why reactivity is going to be highest at the top of the group, because there is going to be less shielding, so it's going to be easier for the nucleus to pull in an electron when there are less electron shells in the way. The marks for these questions are going to be for the 6 things I've written down. So stating the pattern of reactivity, stating that the shielding and that the more shells makes it easier to lose, and then the increased shielding makes it harder for the gap to be filled. Combined Science people, that is the end of your video. Good luck, guys. There are a few more questions for separate science people. Here are 4 more questions for those of you doing separate science. Evaluate the use of nanotechnology. Now, for an evaluate question, we need good things, we need bad things, we need your opinion, and we need why you have that opinion. So, for some of the good things about nanotechnology, it's driving massive advances in medicine, communications, and it is driving advances in electronics. The bad things, people are unsure of new technology. And because it is new technology, we don't know about any side effects. Because we haven't had them around long enough to test it. Now, the tricky thing with this question is just writing the good things and the bad things will get you maybe 4 marks, because if you write this in 4 sentences, you'll have written quite a lot. You have to give your opinion, so you can say, I think that is good or bad. And it really doesn't matter which one you pick, as long as you give a reason that matches your answer and you give a reason. You will not be able to access the top marks unless we start giving reasons. So 2 marks for each section. 25 centimetre cubed of sulfuric acid at 0.1 mole is titrated against 30 centimetre cubed concentration of sodium hydroxide. Find the concentration of sodium hydroxide. First thing we need to do is to write an equation. So H2SO4 plus sodium hydroxide is going to give us NaOH. That is going to give us sodium sulfate plus water. So for titration calculations, I like to make lists. So we have volume, acid, concentration, acid, volume, alkali, concentration, alkali. So 25 centimetres cubed, that is our volume acid. That is our concentration acid. That is our volume alkali. So 25 centimetres cubed. Concentration of acid is 0.1. Volume of alkali is 30 centimetres cubed. So now all the information we need is over here ready and waiting for us. We now need to turn our centimetres cubed into decimeters cubed. So we do 25 divided by 1,000, which gives us 0.025 decimeters cubed as our volume acid. We can now use N equals concentration times volume. Concentration of acid is 0.1 times our volume of acid, which is 0.025. So this is going to give us our N acid. And that is going to be 0.0025. We can see from the equation that 1 mole of our acid reacts with 2 moles of our sodium hydroxide. We can see from the equation that our moles of acid, 1 mole of acid reacts with 2 moles of alkali. So we can say N acid to N alkali is in a 1:2 ratio. So if we have 0.0025 moles of acid, we will have 0.005 moles of alkali. Now we have our N-alkali. We can use N equals C times V again. N is 0.005 equals concentration, that's what we're trying to find out, times volume. Again, we need to do 30 divided by 1,000, giving us 0.03 times 0.03. So 0.005 divided by 0.003 equals concentration. That is going to give us a concentration of 0.17 moles. I know your calculator says 0.16 reoccurring, but we do not do reoccurring in science, so 0.16 is wrong. You need to round it up. So for titration calculations, you're going to get marks for working out the equation. You're going to get marks for working out the correct volumes in decimeters cubed. You're going to get marks for working out the N of the acid and the N of the alkali. Then you're going to get marks for working out the concentration and rounding it correctly. 17.2 grams of salt was made from reaction between calcium oxide and hydrochloric acid. It was expected that 21.4 grams would be made. For this reaction, find the percentage yield and the atom economy. So before we start this question, there is a lot of background work that needs to be done. First of all, we need to write an equation. So we have the reaction between calcium oxide and hydrochloric acid. Now you should know that whenever we react a metal oxide with an acid, we're going to get a salt. In this case, it is going to be calcium chloride, and we are going to get water. Now we can turn that into a balanced equation. This is where you need to know your ions. So calcium is Ca2+, oxide is 2-, calcium oxide is CaO. Hydrochloric acid is HCl. Calcium is 2+, Ca2+, chloride is 1-, minus, so calcium chloride is going to be CaCl2 plus H2O. Then of course we need to balance that by popping a 2 in front of there. When we are working out percentage yield, it is the actual yield divided by the EO ret divided by theoretical yield. So we got 17.2 grams, we are expected to get 21.4 grams. Times that by 100 and we are going to get a percentage yield of 80.4%. For atom economy, we need to do the MR of the useful or the required over the MR of the reactants. Now we need to go to our periodic table and work out the MR of everything. Calcium is 40 and there's one of them, plus oxygen which is 16 and there is one of them. We have hydrogen which is 1 and there's one of them, plus chlorine which is 35.5 and there is one of them. All of that there is 2. Calcium again is 40 and there's one of them, plus chlorine which is 35.5 and there are 2 of them. Hydrogen is 1 and there are 2 of them, plus oxygen which is 16 and there's one of them. So for calcium oxide that's 56, for hydrochloric acid we have 2 lots of them, that's 73, calcium chloride that's 111 and water that's 18. You can add all of these up and you can check that they both add up to the same thing, which is 129. So for atom economy, the MR of our useful, we were looking for the salts, divided by the MR of our reactants, 129, times 100 gives us an atom economy of 86%. Lots of complicated things in here, so the acid equation, working out the formula of the ions, the equation, then working out the percentage yield, working out all of the MR for both of those, and then finally working out the atom economy. How does a simple cell work? So we have solutions of metal ions, so something like zinc sulfate, copper sulfate solutions. And then we have the corresponding metal. They have to be different metals and solutions. In the middle here we have a salt bridge, and this is where our electrons are going to be flowing. Over here we have a voltmeter, so we can measure the flow. And the differences in how much these different metals want to take up or give away electrons will result in the flow of electrons from one side to the other. So the examiner is going to be looking for you to be labelling the salt bridge, talking about movement of electrons, the fact there needs to be different metals, the fact there are going to be solutions and the corresponding metal in there, and then we need to add in the voltmeter so you can actually check that your cell is working. Well done for making it to the end, guys. Let me know how you did in the comments down below, and if you've got any questions, just ask. Ouch. Love you too, Creme.